Hello everyone, this is Gyanshwar Saram Indrala from CSC department, roll number 21951A0552, and this is my maths PPT for AIT Tech Talk, and my topic is Jacobian matrix based observability analysis for state elimination. Let's start. Introduction. Algorithms to determine observable islands and to design a minimal set of pseudo measurements to make the unobservable systems observable or presented. The algorithms make direct use of measurement Jacobian matrix. Gaussian elimination, which makes the whole process of observability analysis simple and effective, is the only computation required by the algorithms. Numerical examples are used to illustrate the proposed algorithms. Comparison of computation expenses and on the Texas systems among the proposed algorithm and the existing algorithms is performed. Index terms, measurement placements, multiple measurement placements, observability analysis, observable islands, trial matrix. Jacobian matrix based observability. Observability analysis as a preprocedure of state elimination must be executed prior to the state elimination in the energy management system EMS. Its function is to decide if the given set of measurement is sufficient to solve the whole system. When the given set of measurements is not sufficient, it must identify all the possible observable islands or subnetworks that can be independently solved, respectively, and a place of minimal set of pseudo measurements to merge the obtained observable islands. Observability analysis has so far been accomplished by the topological and numerical approaches. Topological make use of graph theory to determine the network observability based on the type and the location measurements without any floating point arithmetic. Numerical approaches are based on the decoupled measurement Jacobian matrix and the associated gain matrix. An algorithm is developed to determine all the observable islands if the system is found to be observable. A similar approach is employed to place pseudo measurement to make the whole network observable. Based on the work in equation 8 and equation 9 and equation 19, the factorization based observability analysis and the normalized residual based big data bad data processing have been derived from for state elimination using normal equation approach. All the above numerical approaches need to solve the measurement equations by only investigating the gain matrix instead of the measurement equations. The authors in 11 and 12 developed different numerical observability analysis algorithms to determine observable islands and place pseudo measurements when the system is not observable. These algorithms depend only on the processing of the gain matrix, which results in fewer computations. The algorithm proposed in equation 11 and equation 12 were utilized and applied in 13 and 16 to develop topological approaches and hybrid algorithms for observability analysis. In this paper, numerical observability analysis is restudied. It will be shown that the information about the observable islands can be extracted from the transformed matrix of measurements Jacobian matrix by Gaussian elimination. And so-called trial matrix is defined based on the transformed matrix. Furthermore, the trial matrix, which is defined differently from the test matrix defined in equation 11 and equation 12, is shown to carry the necessary information about the location and the type of pseudo measurements that will merge the above islands. The proposed algorithms can be implemented with minimal efforts in the existing state elimination. The Gaussian elimination is the only required computation. The paper is organized as follows. Section 2 provides an theoretical result for numerical observability analysis based on Gaussian elimination algorithms. Algorithms to determine observable islands and not place pseudo measurements to make the whole network observable are presented in section 3 and section 4. Comparison comparison between Comparison between the existing numerical algorithms and the proposed algorithms is provided in section 5, and section 6 provides the results of test examples. Section 6 Section 7 give the conclusion. Preliminary results. Consider the linear decoupled measurement equation given below. Z is equal to x theta plus e, where Z mismatch between the measured and calculated real power measurements. H decoupled Jacobian matrix of the real power measurements, whereas all bus phase angles. Theta incremental change in the bus phase angles at all bus included the stock bus, plus E measurement error vector. The decoupled gain matrix for real power measured can be formed as G is equals to HTH, where the measurement error coverage matrix is assumed to be the identity matrix without loss of generality. Note that since the stock bus is not included in the formulation, the rank of H A traditional approaches of power systems modeling for observability analysis is used in this paper. That is, all branches impedances are equal to, and the all weighting factors are equal to 1.0. Since the state elimination uses the real parameters, the triangle forces generated from the observability analysis can be used by state elimination. Suppose we have measured and the buses. In order to simplify our derivation, we first need to reorder measurement Jacobian matrix with dimension as follows. Ht is equals to rho hf h of f h of m rho 2 h of n h of r. This is equation 3, where h of f is equals to f cross f by f square and full rank submatrix of h comma f. F is the rank of h of m is equals to f by m minus f. Submatrix contain the redundant part of measurements. H of n is equals to n minus f by f. Submatrix containing the redundant part of modes. H of r is equals to n minus f by m minus f, remaining submatrix in H. Since the remaining matrix HR is linearly dependent on the matrix HM and HN, then we have the following lemma 2.1. We have if we partition the measurement Jacobian matrix H as 3, then we have HR is equals to HN, HF minus 1, HF, HM respectively. Then there exists a non-zero matrix T such that HN, THN and HR is equals to THM. We thus have T is equals to HN, HF minus 1, and the HR is equals to HF power minus 1 into HM. Suppose matrix HF can be factorized as H of F is equals to LU, where L and U are lower and upper triangular matrix respectively. Based on the partition of HT in equation 3, we have the following factorization. HT is equals to rho 1 H of F HF HM rho 2 HN HR is equals to rho 1 L O rho 2 HN U minus 1 I into rho 1 U L power minus 1 L inverse HM rho 2 O is equals to L of 0 of matrix 2 by 2 matrix rho 1 U P rho 2 0 0, where L0 is equals to rho 1 L0 and rho 2 H of n U inverse I. P is equals to L inverse H of m. Now let us study the gain matrix G. When a measurement H of k is added into the existing measurement set, the addition of H of k will be modify existing gain matrix G as follows. G of n is equal to G plus H of k to the power of t. H of k is equal to H power of t h, and hk power of t hk is equal to LO matrix up00 into matrix u power t 0 p power t 0 into L0 power of t plus hkt hk and the following, where q is equals to uut plus ppt and m is equals to L0 inverse hkt. Since upper triangle matrix U is of full rank, the following lemma shows the matrix Q is also of full rank. Lemma 2.2. If U of full rank, then matrix Q is also of full rank. Proof: Q is equals to UUT plus PPT. By solving this, we get Q is equals to U of I plus V0 T UT, where VO is equals to U minus 1P. According to 12 lemma 3.1, matrix Q must be full of rank. Let us partition vector M into the M power T is equals to M1 of T, M2 of T, where M1 is a vector with dimension f into 1 and M2 is a vector with dimension n minus f into 1. Since Q is symmetrical matrix, then it can be factorized into triangular matrix in the form of Q is equals to L1 D1 L1 power of T, and then matrix G can be further transformed as G minus 1 is equals to L0 into matrix of rho 1 L1 D1 L power T 0 rho 2 0 0 plus MM transpose into L0 transpose. By solving this, we get Z power Z1 is equals to L0 L1 dash DZ L1 transpose L0 transpose, where L1 is equals to L1 dash is equals to L1 0 0 I D1 dash is equals to D1 0 0 0 L1 dash minus 1 is equals to L1 power minus 1 into 0 0 I dz is equals to d dash 1 plus matrix L1 minus 1 M1 and 0 M2 into M1 transpose L1 minus transpose T2 transpose H0 is equals to 3 by 3 square matrix row 1 minus 1 minus 1 0 row 2 0 0 minus 1 row 3 0 0 0 and HR is equals to column matrix of order 1 column 1 is minus 1 0 0 and L0 is equals to square matrix of order 2.2 2 by 2 and row 1 is equals to L0 and row 2 is equals to NH U minus 1 I and L0 is that is equals to 6 by 6 square matrix of row 1 1 0 0 0 0 0 row 2 0 1 0 0 0 0 0 row 3 0 0 1 0 0 0 row 4 minus 1 minus 1 0 1 0 0 row 5 0 0 minus 1 0 1 0 row 6 0 0 0 0 0 1. The purpose of defining is that through the study of we could find whether the measurement can increase the rank of gain matrix in words. Suppose if the branch flows measurement actually it is the same logic if the injection measurement, and then study of will provide the information whether or not the branch is observable. If the branch is observable, then connect the increase the rank of the gain matrix. If the branch is not observable, then is able to increase the rank of given matrix. We therefore define to check the observability of all branches the calculation of the branch node incidence matrix for example is necessary. The branch node incidence matrix is construction as follow. Assign a direction of each branch and each row of matrix corresponding to the branch. Each column corresponding to a bus. Therefore, of two measures elements of two row 1 and a bus. If the branch leaves the bus and the bus if branch enters the bus, the order of column is used the form matrix and incidence the bus branches as follows. In the above matrix, each column is corresponding to a branch. The column in a listed in the order of branch 1 comma 2 3 comma 1 comma minus 1 minus 3 2 minus 3 3 minus 4 4 minus 5 and 4 minus 6. Matrix shows that the fourth and the sixth columns are non-zero vectors. Therefore, we know branches 3 minus 4 and 4 to 6 are not observable. Algorithms to determine observable elements. In this section, we will derive an algorithm to determine observable elements based on Gaussian elimination. When the measured system is not observable under a given set of measurements, it can be shown that learn coordinates 4.1 and the 4.2 are also true here. Here expected the statement is little different. Choreography 3.1. Consider a measurement power systems with several observable islands. Number 1. For the pseudo measurements, incidence of nodes belonging to the same observable islands must be zero vector. For pseudo measurements, incident to node belonging to the different observable islands must be a non-zero vector. Inverse. According to the inverse function theorem, a matrix of inverse Jacobian matrix of an inverse function is Jacobian matrix of inverse function. That is, if the Jacobian of the function f of r rises to r is continuous and non-singular at the point p in the r dash, then f is inevitable when the restricted to someone neighbor to p and q. And conversely, if the Jacobian determinant is not zero at a point that there is a neighbor of the point in which function is immutable. The unproved Jacobian construction is related to the global invariability in the case of polynomial functions. This is the function defined by n polynomials in n variables. It is asserts that the Jacobian determinant in a non-zero constant or equivality that is does not have any complex zero, then the function is invertible and its inverse in a polynomial function. Critical points. Critical points. Main article. Critical point. If f of r is to different function and a critical point of f is point where the rank of the Jacobian matrix is not maximal, then the means of rank as the critical point is low the rank of the neighbor points. In the other, let the k be the maximal dimension of the open balls contained in the image of f. Then the point is critical is all minors of the rank k of f are 0. In course of where m is equal to n is equal to k, a point is critical if the Jacobian determinant is 0. Example: consider a function f is equals to r2 equals to r2 with x minus y and f of x minus y given by the f of column matrix xy is equals to f1 x comma y f2 x comma y that is equals to x2 y is equals to 5x plus sin y. Then we have f1 of x comma y is equals to x2 y and f2 of x comma y is equals to 5x plus sin y, and the Jacobian matrix of f is jf x of y is equals to as following, and Jacobian determinant is that of j of f x comma y is equals to 2xy cos y minus 5x square. Other uses: regression and least square fitting. The Jacobian serves a linearized Dizon matrix in statistical regression and curve fitting. See the non-linear squares and dynamical systems and Newton method. A square system of coupled non-linear equation can be solved later by the neural method. Use of Jacobian matrix as systems as equations. Thank you.